Okay, do you see my screen? Okay, so I'm gonna show you a few sample problems today on fluid topic. So we will have a chance to work on the sample problems just like the last session. And um, this is just additional problems on the fluid because you have scheduled for the test on this topic too, right? So we'll just walk through that the example problems today. So let me maybe read these first problems, and then we'll just work on each problem step by step. So the number 16, snorkeling by humans and elephants. When a person snorkels, the lungs are connected directly to the atmosphere through the snorkel tube and thus are at atmospheric pressure. In the atmospheres, what is the difference delta P between this internal air pressure and the water pressure against the body if the length of the snorkel tube is A, 20 centimeters standard situation, and the B, 4-meter, probably lethal situation. In the latter, the pressure difference causes blood vessels on the walls of the lungs to rupture, releasing the blood into the lungs. As depicted in the figure 14-31, the elephant can safely snorkel through its trunk while swimming with its lung 4 meters below the water surface because the membrane around its lungs contains connective tissues that holds and protects the blood vessels, preventing the rupturing. So in order to solve this problem, you have to understand there's pressure is normally in this situation only depend on the kinetic energy of the gravity because there's no water floor mentioned in the problem. So in the Bernoulli equation, you have to just use the simplified version of the formula, so you can actually find out the connection between the pressure and the depths of the water into the surface of the water too. So basic formula to solve this problem is pressure at certain depths should be pressure, it could be expressed with the pressure at atmosphere plus the potential energy term regarding the depths into the water, surface of the water. So this is external pressure at a depth H without this snorkel 2. Okay, that's standard formula. So as I said, there's no 1/2 low v squared term because there's no flow of water, no flow of water described in this problem. So this only depends on the depths of the water into the surface of the water too. So if you move that the P naught, atmospheric pressure to the left side, then that should be, so P minus P naught, that is delta P. The pressure difference between the surface of the water and the one into the water with the depth H. So that is just proportional to the density of water times depth of the water. So now number A. Now H, how much is it? 20 centimeter, right? So 20 centimeter is same as 0.2 meter. And density, in this case, just normally 1,000 or sometimes they use 998. pretty close to the 1,000 kilogram per cubic meter. I'm just using this number to plug into this formula. Then that is 998 kilogram per cubic meter times 9.8 times meter per square second times 0.2 meter. You plug all those numbers into this formula, then that lead to the answer of the pressure difference. So that is then also at the same time you have to actually change the unit from Pascal to ATM. So unit conversion scale factor of unit conversion is 1 ATM times 1 ATM. It corresponds to the 1.01 times 10 to the 5 Pascal. You plug into this scale factor of unit conversion, then that should be same as 0.019 ATM. Okay. Mm-hmm. So that pressure underneath of the surface of water with the 20 centimeter. Problem B is the same as the problem A, is exactly the same. So you want to solve the problem B with the same way.
Okay.
All right.
I got 0.387 ATM.
That's correct. So that is about 0.39 ATM. So only difference is the depth of the water, right? That is 4 meter instead of 0.2 meter, right? So if you plug into this formula, you should be able to get that answer. Okay, let's move on to. You have a question, or no. Okay, that's just straightforward. Can you read the number 27, the next page?
What would be the height of the atmosphere if the air density A were uniform and B decreased linearly to 0 with height? Assume that at sea level the air pressure is 1 atm and the air density is 1.3 kilograms per meter squared cubed.
So basically, this problem is pretty similar with the one we solved, but instead of constant density, the number of density is constant in the given circumstance, like ambient fluid or liquid, normally considered to have the constant value of density. But now this problem just set up the three different cases. No, actually two different cases, like uniform density and some functionalized density with the linear relationship with the depth or height of the atmosphere. So you have to still use the same type of formula. The Bernoulli equation, but with the only potential energy, not with the kinetic energy term. So standard the formula. So if the air density is density was the uniform, then doesn't change with the height, then low must be the constant value. has nothing to do with the height of atmosphere. So with that condition, pressure at certain point should be expressed with the pressure at reference point and the potential energy difference between the two different positions, H1 minus H2. So that is delta H, height difference between the two different points. So then if the case 1 and the case 2, but if the density decrease linearly with the height, then let me move this one. Then the density profile should be given like this: the low constant density, the reference density at the reference point minus 1 and 1 minus y over h. So here y is variable of height. So depend on the position where you're actually standing, you have the different amount of the density corresponding to the position. So if you plug that into the standard formula of the Bernoulli equation, only with the potential energy term, then that should be P2 equals P1 minus integral of 0 to the h times low y dy. You plug, this one is low y. So you plug that into this formula, then that should be P1 minus 0 to h low naught 1 minus y over h dy. So now you know how to just integrate this equation, right? So that should be P1 minus 1 over 2 low naught g h. Okay, you see the difference between two expressions with the two different conditions. One with the constant density, and the other one is linearly varying density profile. So now let's solve the first one with the first condition. So let's see. All you need is actually plug the numbers into this formula. So what do you have to do here? In the case for oh, sorry, this one is the y, y2 and y1. Oh, so gotta be y2. Oh, that's something. That should be variable at the two different y2 minus y1. Okay, so now a, you want to find out, the question is we got to find out the height of atmosphere for first case uniform density, and second case decrease the linearly to the 0 with the height. So the height itself is y2 minus y1. So that if you rearrange the equation from the number 1, then that should be P1 over low z. And then number B, what are you gonna do? That is the same. P2 minus is the P1 minus low GH2. Same. Now the P1, I mean the P2 here, set the linearly to 0. So the final atmosphere at the height h, the P2 is equal to 0. We plug it into this formula, then h should be 2p1 over low naught z. So why don't you plug the numbers and tell me how much you got for problem A and problem B now? So make sure you put the air density 1.3 kilogram per cubic meter. Not mixed up with the water density, just like what you did the last session. Okay.
For A, I got 0.078.
Okay, A is how much did you get?
0.078.
0.078. What's a unit?
Meters. Point
Meter?
078.
Meter?
Yeah. But there's a 0 in front of the 7.
Points. Oh, 0 or points?
0.078.
78?
Yeah.
Okay, let me get your answer for B2 and then I'll just go back to the A.
0.157.
7 meter?
Yeah.
Okay, that is the 3 orders magnitude is smaller than what I had. So, okay, let's check. So P1, that P1 is, gotta use the Pascal unit, right? That's 1.01 times 10 to the 5 Pascal. That is the atmosphere at reference point. And the low is what? That is 1.3 kilogram per meter. And oh, yeah, then G is 9.8 meter per second squared, right?
Mm-hmm.
To plug that, then it should be 1.01 times 5, 1.3, let's see, 10 to the 3 times 9.8, right?
Yeah.
So this is 2, that is 101 divided by 1.3 divided by 9.8. That's got to be more than 0.078, isn't
I
it?
forgot to convert the ATM to kilograms
Okay. Oh,
per.
okay. Do you want to just then resolve the B with that
Yeah.
same unit? Can you do it?
After resolving it, I got 1.57 times 10 to the 4 meters
1.57.
times 10 to the 4 meters.
Okay. That sounds like correct one. All right. Okay. And that's it. Any question?
No.
Okay. Then let's move on. Number 31, the block of wood floats in the fresh water with a 2/3 of its volume V submerged and in oil with the 0.9 V submerged. Find the density of the wood and the oil. So submerged part of this wood is 2/3 of the total volume. So you express that submerged portion in the water, then that is just 66% of total volume of wood in the water. In water, that is 2/3 V. Here's V is total volume of the block. So Archimedes principle indicating that the density times volumes in the ambient fluid is conserved. So that should be same as the total quantity of the density times volume should be same as the total volume times total the density of the material itself into the fluid. So if you express that description into mathematical formula, then Archimedes principle should be like this: density of the fluid replaced by the object floating in the the fluid is the same as gravitational force, which is, I mean, yeah, the object. So here, this one is density of water, and this low B is density of a block. So with that idea, you can solve number one, A. So low B times total volume of the block is same as low W Vs. So you replace low W, the Vs with the two-thirds of total volume V. Then low B, the density of block, to be just two-thirds of density of water. So that is just, so how much is the, okay, so the density of the water now, let me just use that the 1000 kilogram per cubic meter, then two-thirds will be the 6.7 times 10 to the 2 kilogram per cubic meter. Okay, that's easy. And now if you replace water with the oil, the ambient fluid change to the oil from the water. So water is replaced to the oil. Then the density of oil times the volume of the block replaced by this oil is the same as the gravitational force to the block. So low B times B. So now you replace this Bs. That is 0.9 V, the 90% of total volume. So Bs should be 0.9 V. Replace that, then low not times 0.9 V for the low B times V. The V, low oil density, is proportional to the density of block multiplied by the ratio of volume between those two portion, total volume and the submerged portion. So that is 7.4 times 10 to the 2. So 740 kilogram cubic meter. Okay, that is easy problem to solve, pretty straightforward. All we need just replace the background material, the fluid, with the with the oil. So that's all we need. Okay, let's move on then. I don't think you have any problem with this.
No.
Okay, so can you read number 37?
Yeah. A hollow spherical iron shell floats almost completely submerged in water. The south diameter is 60 centimeters and the density of iron is 7.87 grams per cubic centimeter. Find the inner diameter.
So let me draw the picture of this circumstance. So now you have hollow spherical iron shell just float in water, but they completely submerged. So if you draw a picture of this hollow shell, it should look like this. There's some shell, but they gotta be like radius, outer radius, but because inside of this sphere shell is completely empty, so there should be outer radius r out and radius r in. Okay, so the density of iron, this is the iron portion, is low iron is 7.87 gram per cubic centimeter. All right, that's what is given in this problem. And submerged part of this total volume. Do you know the equation of the volume of spherical shape or sphere?
4/3 pi r cubed.
Yes. So volume submerged into in water should be total volume of this hollow spherical ion shell. So that is 3 or 4 4/3 of pi r radius squared. That is submerged part. So only outer radius is in this formula because that the total volume is defined by our radius. So now diameter of this spherical shell, outer diameter is 60 centimeters. So inner outer radius is 30 centimeter, which is 0.3 meter. Now, based on Archimedes' principle, the density of water, the water, I mean like the plate, the part replaced by the part of the water replaced by this the spherical shell is the same, should be the same as the mass part of this the spherical shell, the gravity, I mean the weight of this spherical shell. So the water times G times V submerged should be same as the low ions, the density of ion times G times. So the net volume of this spherical shell should be outer volume subtracted by the inner volume. So that should be net volume should be 304 pi r outer radius minus 304 pi r inner radius cube, right? If you plug that into this formula, then that should be of 3 the pi r outer radius cubic radius and minus the 43 pi r inner radius cubic. Okay.
Mhm.
So next step, the question is you have to find out the diameter. So everything else is already given in this formula. So this Ri is variable, unknown variable that you have to find out. So can you summarize, rearrange this formula in terms of Ri and then plug in the numbers and then tell me how much you got.
Mhm.
You're still working on it?
Yeah.
Mhm. You need more time?
Yeah.
Okay. So that one extra hint is this submerged, actually this one. You're gonna plug it into this formula. So the left-hand side, this formula is W water Z video 4 pi R up radius of the outside. Um, with, yeah, our radius cube. Hey, do you want me to show you the answer and solution, or do you want to take more time?
I think I can do it.
Okay. What about now?
I got 1.038 meters.
1.038 meter
For diameter.
for diameter. It's like just twice bigger than the number. So it wouldn't be like this number because you see that the outer radius only 60 centimeter, right?
Yeah.
They cannot be bigger than that, right? Centimeter. So let me show you how to. Probably you just have a slight mistake in the math. That's it probably. So if you just come look at this formula, right? So that just g, we can cancel the g out of the both sides of the equation, and that is the low w, 4 pi r naught q is a low iron, 4 pi r naught radius outer radius cube, radius time in the minus, and inner radius cube, right? And now you can also take this off too. Out of this formula, there's this common term. So if you divide both sides with the low iron, then there should be low water by low iron. And you also divide both sides with r outer radius cube, then that should be low the outer radius cube divided by outer radius cube minus inner radius cube minus outer radius cube, right? And this one is 1, okay? So if you move this one, so that should be 1 minus Ri over R not, R outer radius cube. Are you with me? Okay, then now we just move this one to the left-hand side and then just plug the minus sign both sides of the equation. That should be I over R O cube equals 1 minus low density or low iron. Now you take like the power of 1 over 3 the both sides, then Ri or R naught cube over power of 1 over 3. Also, that is 1 minus low W or low iron 1 over to the power of 1 over 3, right? And this the cancel, and that lead Ri over R naught equals 1 of low W or low iron to the power of 1 over 3, and you just moved R O outer radius to the right hand side, then R I should be R O times 1 of low W low iron 1 over 3. So all you need now is plug in all the numbers. So RO is 30 centimeter. Water density is what? It's got to be 1. That should be 1 gram per cubic centimeter. That is corresponds to 1,000 kilogram per cubic meter. So that is the same. You plug that here, 1 gram per cubic centimeter, and the density of iron is 7.87 gram per cubic centimeter. If you plug all the numbers, that should be now, and also you have to multiply by 2 at both sides because that is diameter, right? We multiply by 2, then, so that is 57.3 centimeter. That is, diameter. Okay, slightly smaller than the outer shell, I mean outer diameter of this shell. Okay.
Mhm.
Do you have any question about the solution, the weight, just to derive the formula?
Not right now.
Okay, you may want to review the derivation,
Yeah.
and if you have any question, let me know. Okay, let's move on to the next one. So let me read this problem. So when the researchers find a reasonably complete fossil of dinosaur, they can determine the mass and weight of the living dinosaur with the scale model sculpted from the plastic and based on the dimensions of fossil bones. The scale of the model is 1 over 20. That is, lengths are the 1 over 20 actual lengths. Areas are 1 over 20 to the power 2 actual areas, and the volumes are 1 over 20 cube actual volumes. First, the model is suspended from the one arm of balance, and the weights are added to the other arm until equilibrium is reached. When the model is fully submerged in the water and enough weights are removed from the second arm to reestablish equilibrium, full model of the particular T-Rex fossil, the 637.76 gram, had to be removed to re-establish equilibrium. What was the volume of the model and the actual T-Rex? And that's number B. And C, if the density of T-Rex was approximately the density of water, what was its mass? So we gotta first find out what is going on here. So you already know the actual weight, but if you put that object into the water, your measured weight is different from actual weight by buoyant force, right? So the first step is to find out the the difference in the weight between the actual and the one in the water. So that could be expressed with this formula. So number A, actual weight minus the one supported by the buoyant force is the difference in the mass, right? So this is, let me change the color. Actual mass. The first term is actual, the actual weight in the air. And this one, second term, the one measured in the water. So that in the water, okay, that is difference between those two and the weights. And now, if you re-simplify this formula, you can take the Fg minus Fb out of the bracket, then that should be Fg minus Fg plus Fb is mg delta mg. The weight difference between those two methods, so that Fg, they are just cancel each other. So buoyant force is just weight difference. So also buoyant force could be expressed with this formula. Buoyant force is self-defined by mass of the water, ambient liquid or fluid, times G times volume submerged in the water replaced by the object. So if you plug into this formula, so that left-hand side, this formula number one, left-hand side number two, they're all same. So the right-hand side must be same too. So from there, the low density of water times G times volume of the object must be same as delta mg, mass, the weight difference. So from that, you can easily find volume, the number A, the question. You're gonna find the volume of model. So that is just model fully submerged into the water. So the volume of model submerged, fully submerged into the water is the mass difference, weight difference. It keeps you saying that mass, it should be weight. So the weight difference divided by density of water and G. Okay, so all you need to plug the numbers. So that delta mg, where is it? That is 637.76 grams. That is 0.63776 kilogram times oh, actually, you know what? This G could be canceled out of the denominator and numerator. They cancel each other. So all you just have like mass difference divided by density of water. That's all you need. And you plug the density of water, which is 1,000 kilogram per cubic meter cube. And that is about 6.378 and 10 to the minus 4 cubic meter, right? That's number 8. That's volume for the T-Rex fossil model. And number B, actual T-Rex. You have to find out how much volume actually T-Rex has by apply the scaling factor. How much is the scaling factor in this problem? The length. In length.
1/20.
So the actual T-Rex must be 20 times bigger in length, right? Mm-hmm. So number B, scaling factor is in the length one dimension is 1/20 times bigger. Actual T-Rex is just, this is scaling. Oh, scaling factor. So this is for one dimension in length. If you just estimate the volume scaling factor, then you have to just take a cube of this number, so that we're gonna just cube the number. So that is volume. Actual dinosaur is 20 to the power 3, 20 cubic, the 20 times the volume of model should be total volume. So that volume is 6.38 times 10 to minus 4 cubic meter. I plug it and then just multiply by 20 to the power 3. So that is what, 5.102 cubic meter. That is volume of actual T-Rex. Okay, number 3. So if the density of a T-Rex was approximately density of a water, what was its mass? Well, you just need to apply the definition of density. The density itself is mass divided by the volume. So you just need to divide the mass of the dinosaur T-Rex by the volume of dinosaur. So that should be same as water. That's condition, which is 1,000 kilogram per cubic meter. So we know. So that's what you have to do. Mass of the dinosaur is the density of water times volume of dinosaur. So that is 1,000 kilogram per cubic meter times volume is how much? Is 5.102 cubic meter. So that total mass of this dinosaur is 5.102 times 10 to the 3 kilogram, about 5 ton. All right? Mm-hmm. That's number C. Okay. Any question regarding this problem? Okay, then let's move on